Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Hello, welcome to Pytorch tutorial series. Today we shall implement recurrent neural network on an image dataset, that is MNIST dataset that we have used to demonstrate our previous few videos. So today's video is about showing the fact that RNN can also be used to learn features from the image dataset, but the format of presenting the data is a bit different. So let's jump into it. So to implement recurrent neural network in Pytorch, you have to import torch, torch.nn, torchvision.transforms to transform a dataset into tensors, torchvision.datasets to import the datasets into our system. We are calling the datasets.mnist to download the training dataset and testing dataset. You might remember from the previous videos that the training dataset is 60,000 images of digits and test dataset is 10,000 images of digits, and each image has a size of 28 by 28. This information will be important later. As usual, like we have used in some previous videos, the batch size is 100. Number of iteration is 3000. Now, our idea here is to iterate over the whole dataset in 3000 iterations, but we define the number of epochs like this. So the whole training dataset that is 60,000 images is divided into batches of hundreds, and so it will give you 600, and total number of iteration is 3000, so the number of epochs is 5. Hence we will cover the whole dataset 5 times in a series of 3000 iterations. We also call the train and test loader. Let's see how to build the basic RNN module. To build an RNN, I have given it a name RNN model. Try to give it a meaningful name. Inherit nn.module that has all the properties of deep learning in Pytorch. Inside the init function, I have called the input dimension, as in the dimension of input dataset, the hidden dimension, as in number of neurons in the hidden layers. Layered dimension is basically how many layers, how many hidden layers I want to insert in each of the RNN module. You might remember from the previous video that there are multiple RNN modules for each time instance, and each of them are identical to each other. So they are all similar. In fact, they are all same. It's just how many layers do I want. Then there is output dimension, in meaning that how many outputs do I want. Of course, the output dimension is basically your number of classes. In the second line, we call the constructor function, which is basically super that calls itself. Then we specify the hidden dimension, the layered dimension, and finally we call the nn.rnn method in Pytorch. It has all the components that we have called in the init function, that is input dimension, hidden dimension, layered dimension. Batch first true is useful. Try to make it true all the time, since it gives a certain dimension to the output that we need, as in it puts the number of batches as in 100 at the beginning, otherwise it will put it at the end, which we don't want. Non-linearity is basically the activation function that we are using in RNN. Here I have written tan-h. Tan-h is one of the very good activation functions. I have mentioned that in the previous video. We can also use ReLU function, that is rectified linear unit. I'll talk about these activation functions in a separate video. Let's keep it tan-h for this purpose. And of course, the last layer is a linear layer that has hidden dimension from the previous hidden layer and the output dimension. In our case, the output dimension is 10 because we have 10 classes. In the forward pass, I have mentioned that in the forward pass, we feed the hidden layer from the previous RNN module to the next RNN module, and here I've mentioned H0, that is the RNN input hidden layer units are set to 0, so I have called torch.zeros, and of course it has a dimension of layer underscore dimension and hidden dimension. So I'm initializing my hidden layers to zeros, and this line out comma hn is helpful for back propagation. You might remember from the previous video that we back propagate over time in RNNs, as in we have to back propagate for every RNN module in the whole RNN system, and each of the RNN module stands for one time instance. So basically it's back propagation over time. And when we perform back propagation over time, there is a tendency for our gradients to either explode or vanish. To prevent that, we use h0.detach, and this whole thing will take care of the output and the input to the next layer. So the whole thing is covered here. Now of course we have the output that we use in the forward pass. Okay, now input dimension is 28 instead of 784, unlike CNN, which I'll discuss in a minute. The hidden dimension is 100. Layer dimension is 1, meaning there is only one layer in each of the hidden module, and there are 100 hidden dimensions. And the output dimension is of course 10, so we call this. We define our CUDA device. Since we are on Google Colab, we can take use of that. The loss function is cross entropy loss, which I have mentioned multiple times that it's a very good loss function. Learning rate is 0.1. Optimizer is SGD, which is sufficient for our purpose. The sequence dimension is 28. I've mentioned that input dimension is 28. The reason is you can think of it as sequence dimension is each time instance. So basically you can think that at each time instance I'm inserting one row of the 28 by 28 image. So by doing that I can cover the whole 784 pixels, and at each time instance I'm inserting 28 pixels of only one image, and that is being done for 100 images. So after this we train our model, which I ran just a second back so that we don't have to wait for it. So final accuracy is 85%, which is really very high. Thanks for watching.